And many thanks to the organizers for their kind invitation. So today, the topic of my talk is the delta symbol and how one uses the delta symbol to solve the problem of arithmetic correlation. Okay? So let me first define what I mean by an arithmetic correlation. So given two arithmetic sequences, so suppose an is an arithmetic sequence and bn is another arithmetic sequence, we want to understand the sum that you get by you multiply n with bn and take a sum over n. Okay, so so don't worry. A little later we'll be just taking a finite sum, so our sequence is going to die down after some point. So there will be no problem with divergence or convergence. Okay, so this is the sum we are interested in, and if the interesting arithmetic sequences that we'll be looking at are the following. So one is the very simple thing, which is n to the power it, and where t is some real number and n is varying. So t is fixed, possibly large, and n is varying. Or you can look at the sequence of chi n. So this is something periodic where chi is a Dirichlet character modulo some modulus say q, and so it's periodic modulo q, and these chi n's are lying on the unit circle. Or we may be interested in e of pn. So here we are using the standard notation. Ez is e to the power 2 pi I z, right? And p over here is some real valued function. You can take a polynomial with rational coefficients, for example. And the next one, lambda fn, this is more interesting. These are the Fourier coefficients for so normalized Fourier coefficient for a modular form or a mass form. So this small f over here is a modular form or a mass form, and these are the normalized Fourier coefficients. All right, or we can take pi to be a higher rank automorphic form, for example, for SL3Z or SL4Z, and we look at the normalized Fourier coefficients lambda pi n. So I'm just varying n and keeping the other variables here fixed at 1. Okay, so if it is a GLD form, then there will be d minus 1 many entries over here, right? Okay, and then so for example, we can take our an to be like 1 and bn to be n to the power it. This type of arithmetic correlation appears when you want to study the size of the Riemann zeta function, so zeta half plus it. Or you may look at an equals to 1 and bn equals to chi n, and this type of sums, correlation sums, appear when you're looking at studying the size of the Dirichlet function at the central point. Okay? Or you may take an to be lambda fn, the Fourier coefficient of some GL2 form, and bn to be n to the power it. This type of sums arise when you're looking at the size of the L function on the central line corresponding to the modular form or the mass form f. Okay, and the next one is where this is the Fourier coefficient, this is the Dirichlet character. This arises when you are studying the twist of the modular form by the character chi on the central line. The last two are slightly different. They do not come from an L function as such. So this, the fifth in the table, corresponds to the problem of looking at, it's called the generalization of the Dirichlet divisor problem. So if you're looking at the sum of lambda fn, okay, say n going up to x, and you want to bound this sum, okay, what's known is bounded by x to the power 1/3, and you want to get something better. So to get something better, you have to look at this type of correlation sums, where an's are Fourier coefficients of this form f, and bn's are e of root nx. Okay, and the last one over here, where here pi is a SL3Z form. Say pi can be a symmetric square lift of a GL2 form, for example. Then this type of correlations appear when you're looking at when you're trying to show that there are infinitely many zeros of this corresponding L function, say L is pi, on the central line. So when you're trying to prove something like the Hardy's theorem. Okay. So these are some instances which I'll come back later and say more about them. Okay. So now, okay. So in the main problem of arithmetic correlation, so as I said, there will be some conditions on the arithmetic sequences. For example, we are going to assume that they are supported in some dyadic range. Okay, so between capital N and 2n. So beyond that, they are just vanishing, right? And we can also assume that the sequences are bounded by some n to the power epsilon. So it's like bounded by a divisor function type of thing. If it's not pointwise, at least we need it in the L2 sense. Okay, so that if you look at sum of absolute value of n square, say n going up to capital N, then it is bounded by n to the power 1 plus epsilon. Okay, and we also assume that at least one of the sum of an and or sum of bn is small in the sense that it is of size n to the power 1 minus delta. Okay, trivially, because of our second assumption, trivially it is bounded by big O of n, and we want that there is some cancellation like n to the power 1 minus delta. Okay, then the correlation, the usual definition of correlation is this one, right? So you take this product, take the average, and subtract the product of the means. And then this can be written in terms of S as S by n plus big O of n to the power minus delta, because we're assuming one of them, one of this or this is bounded by n to the power minus delta. Okay, so what we are interested in is showing that the arithmetic sequences are independent. And by that, what I mean is that I want to show that there is some cancellation in this sum a and bn. Okay, so trivially, this is bounded by n, and we want to show that it's bounded by n to the power minus 1 minus delta for some delta positive. Okay. Okay, and the usual philosophy is that if you have two different oscillating sequences, if they're coming from two independent sources, like one is coming from a Dirichlet character, the other is coming from a modular form Fourier coefficient, then they are necessarily independent. Okay, so that's the usual philosophy. For example, if you take one to be coming from the Fourier coefficients of GL2, the other one coming from the Fourier coefficients of GL3, then they will be independent. Okay, so as I said, that we are interested in such type of arithmetic correlation because this type of sums arise often in analytic number theory. As I mentioned before, the one important source is the subconvexity problem. Okay, in the subconvexity problem, it's about bounding the size of the L function of any L function inside the critical strip. And I'll come back to the details about this because I'll spend some slides on this problem. So there is something called an approximate functional equation, which comes from the functional equation of the L function, which boils down the problem to computing certain correlation, as you'll see. Okay, so the other problems that are related to computing arithmetic correlations are, for example, the shifted convolution sum problem. This is also something which is related to subconvexity. If you are using the moment method to study subconvexity, this type of sums arise normally naturally over there. Okay, so here I'm looking at the GL2 cross GL2 shifted convolution sum problem. Both F and G over here are GL2 automorphic forms, and I'm looking at the normalized Fourier coefficient. So I'm shifting one of them by a fixed number H. Okay, and even if F equals to G, since I'm shifting by a number H, there should be some cancellation in this sum. Okay, so that's called it's a general shifted convolution sum problem, and this is also related to what is called an arithmetic quantum chaos or quantum inequality. Okay, so the other one is the Dirichlet divisor problem. The classical Dirichlet divisor problem is that you look at the sum of the divisor function, say n going up to x, and Dirichlet gave an asymptotic, so it is x times some log x minus or plus 2 gamma minus 1, something like that, plus an error term, which I write as delta x, and Dirichlet's problem was to get a bound for delta x. He proved the bound that it's bounded by x to the power 1/2, and it was conjectured that it's bounded by, it's still a conjecture that it's bounded by x to the power 1/4 plus epsilon. And what is known is something near x to the power 1/3, a little less than x to the power 1/3. And if you want to really improve, go much beyond x to the power 1/3, then you have to look at this type of correlation sums, okay, where one of them is just the divisor function. So here I'm looking at the general divisor function of order k. If you take the usual divisor function, then k equals to 2. And then here we have an exponential. Okay, and there is also a cuspidal analog, as I mentioned. If you take a modular form or a mass form, and you're interested in summing the cusp form, sharp cut at x, then then it's also expected that this is bound. There is no main term here because it's cuspidal. We expect that this is bounded by x to the power 1/4 plus epsilon. This is the conjecture. And what is known that it's bounded by x to the power 1/3. And if you want to go beyond x to the power 1/3, that's a very important, a difficult problem in analytic number theory. You have to study correlation sums like this, okay, and you have to show that there is cancellation. Okay, so where the length of the sum is quite small compared to the oscillating factor. Okay, so n is like x to the power 1/3, and the oscillation is like square root of nx. It's quite large. Right? So it's quite a challenging problem. The other one is, as I said, that if you're looking at the critical zeros of symmetric square L function, then you will get this type of sums, and then your problem will be to show that there is a significant cancellation in this sum. You want to show that this is bounded by n to the power 1 minus 1/6 minus something extra, or something positive. Okay? Or at least you want to show that this is little o of n to the power 5/6. That will also give what's called Hardy's theorem for symmetric square L function. Okay. The other problem is what's called the linear twist. So if you look at in the GL2 scenario, if you look at lambda fn, so these are the normalized Fourier coefficients of GL2 form Enx, then we know square root cancellation here. So yeah, so suppose n is of size x, sorry, I'll say, let me call it alpha, n alpha, then it is bounded by square root of x, or x to the power 1/2 plus epsilon. That's what's known. It's quite easy actually to prove in case of GL2. But if you go beyond, still it's conjectured that there will be a square root cancellation in this type of sums. So the conjecture is that this is bounded by n to the power 1/2 plus epsilon. But so far, using the Voronoi summation formula for GL3, one is able to prove that it's n to the power 3/4 plus epsilon. Okay. So yeah, so it's yeah, so this is another challenging problem that you get. And if you want to look at higher rank exponential sums, these are correlation sums of this type. Okay, and here beyond, if you're looking at pi GLD form, then for d greater than or equal to 4, this is completely open. Okay, there is no non-trivial bound known in such cases. There's a range for beta where you can just trivially get some bound, but you really want to push beta beyond the trivial range, and nothing is known for GL4 and beyond. Okay, so now let me describe how we are going to get cancellation or show cancellation in a correlation sum. Okay, so as we start with two arithmetic sequences which are supported in between n and 2n. Okay, so we can think of them as functions in some space. So that space is called V over here. We're looking at collection of all functions from this domain to a complex valued function. So this is a vector space of dimension n, right? Roughly, because there are n many points of summation here, n many points over here on the domain, and then if you take two arithmetic sequences supported between n and 2n, you can think of them as elements in the vector space V, and then the correlation is just the inner product of A and B bar. Right? So we want to compute the inner product. We want to show that there is some sort of orthogonality over there. Okay, and yeah, and suppose we have an orthonormal basis, then there is a formula to compute the inner product. Okay, so instead of computing the inner product of A and B, we can compute the inner product of A with the basis elements and the inner product of B with the basis elements, and then sum over the whole basis. That will give you the inner product of A and B. Okay, that's a simple linear algebra fact. Okay, but we can use this here. Okay, so once we have such a basis, then our plan will be to analyze these two sums separately. Okay, so here we have decoupled the sequence A from the sequence B. So now I want to apply some sort of summation formula that should be available to us to this inner product, to evaluate this inner product. So this is actually, by definition, is this. And then by some summation formula, it gets transformed into something like this. Okay, I'm not going to specify what n star or a star n or psi b star n are. It will depend upon what sequence you were starting with and what type of basis you were picking. Okay, okay, and we do the same thing for the other sequence also. And so the sum S reduces to something like this. For the other sum, the length becomes m dagger by definition. Okay, and next, so I have used two summation formulas, and then I apply Cauchy's inequality. Okay, so I take one of the either the n sum or the m sum outside, put the rest inside the absolute value, do Cauchy. Okay, and this is what you get by Cauchy inequality. And then the next step will be to open the absolute value square and bring the n sum inside and apply some summation formula yet again. Okay? And this time the summation formula should be something much easier, right? So that's the recipe. Okay, so I use a basis, I separate A and B using a basis, I apply summation formula for A and B separately, I come back and then apply Cauchy and open the absolute value square and apply another summation formula. Right? Okay, so now how do you get an orthonormal basis? So I'm looking for sequences psi vn. So for each element in vector in the basis, I want psi vn to be a function, and which has this type of relation. Okay, so that their inner product should be 1 if their same v equals to w and 0 otherwise. That's denoted by the delta symbol. So this is equal to 1 if v equals to w and 0 otherwise. Okay, and then from the usual property of orthonormal metrics, we know that that the same thing as saying the following. So here the sum was over n, here the sum was over v. So instead of looking at the inner product between the columns, you're looking at the inner product between the rows, and this is the property that you need. Okay, so that means that if I have a collection of functions which satisfy this property, that this sum is delta nm, then I can write my correlation like this. Okay, and now this is something which is quite classical, because this goes back more than 100 years to Ramanujan, right? So this comes from what is called a circle method, the delta method. This is what we are doing, is we're trying to expand the Kronecker delta symbol in terms of some harmonic functions, right? So what Ramanujan did is he used the harmonics of the circle group, or what are called the trigonometric functions. And one modern form of the circle method due to him is called the delta method. Okay, and the delta method, if you look at the just the bare minimal form of the delta method, it's basically this. Okay, it says that delta nm is more or less, this is not really an exact formula, is 1 by n. So my n and m are in the range capital N, between capital N and 2n. Then my q has to go up to root n. This is the modulus. And then I have a sum of a modulo q. The star implies that a and q are co-prime. And then I have e n by q and e am by q bar. Okay. Again, ex is e to the power 2 by ix, as I mentioned earlier. So now from here, what is my psi v and this function psi vn. Okay, so that is so v is now for me is going to be this pair aq, right? So q is up to root n and a is modulo q. So there are like roughly n many vectors over here, and for each vector psi vn is given by 1 by root n e of an by q. Okay, that's just the trigonometric function. Okay, and this the delta method says that this has this required orthogonality relation, and so this can be used to separate the correlation. Okay. Okay, and as I said that this is an oversimplification. The delta is not exactly equal to that. The original DFI formula it looks like this. Okay, so where I was just writing up to this part. Okay, and there is a function which is not really bad if you pick your modulus going up to root n. Okay? If you pick your modulus smaller than root n, then there will be a lot of oscillation in this function, and you have to control that. Okay? But it's not really a problem. It's not really very explicit, but if you look at the Fourier transform of that, that's kind of well behaved. So it's not bad. Okay. So this was given around, this formula was written down around 1990s. But if you, there is also a classical form due to Clusterman, which is almost equally as good as this in certain situation. So this is called the Clusterman's circle method. And here also you have a choice for Q. Okay, you pick a Q, any number greater than 1. Then you have this exact formula that the Kronecker delta symbol is twice the real part of this integral. Okay, and now here you'll see, all right, so this 1 by q is basically this 1 by aq, right? And then this was the Ramanujan sum over here. So we have the Ramanujan sum over here, but the main thing is that the arithmetic parameter, also appears on this side. So here the arithmetic side and the analytic sides were separated. Here the arithmetic and analytic are intertwined, but it's not really a big problem in certain situation. Okay? And the plus point of Clusterman formula is that the analytic part is completely explicit. Okay, so this is the second. So this is the formula number 1 for delta. This is formula number 2 for delta. We can have higher rank expansions also. So up to this, we had been writing delta in terms of trigonometric functions, but we also have what's called a Peterson trace formula, right? So yeah, so which says that, maybe I'll just make it a little smaller. Yeah. So if you have so you're looking at the space of cusp forms of wet K, level Q, and event type psi, right? And this HKQ psi is the Hecker basis for the space of cusp forms. And then I'm looking at, I'm summing over F. So these are some spectral weights I'm not going to specify. Basically, the Peterson trace formula says that if you look at the sum of the Fourier coefficients of this modular forms over here, lambda fn bar, then it is equal to delta nm minus a sum which involves the Clusterman sum and the J-Bessel function. Okay, so this gives you a nice expansion of the Kronecker delta in terms of Fourier coefficients of GL2 forms and Clusterman sums. The Clusterman sums you can open up, and they are also can be written in terms of trigonometric functions. Okay, so this part is what more or less what we had before. So this we can say is the GL1 part of the formula, and here we have a GL2 part. Okay, and then you can do some more averaging in this formula. For example, you can average over the Niven-Tippers, you can average over the level, you can average over the weight. If you do that, then it reduces or it gives you this expansion, which looks much more complicated, but you have more points of summation in this expansion of the delta and the same conductor. So it helps you a lot if you have do those averaging. Okay, so that's an expansion of delta in terms of Fourier coefficients of GL2. We can also do a Fourier expansion for with respect to GL3 Fourier coefficient, okay, which is called the GL3 Kuznetsov-Tress formula, and it's slightly complicated. So there will be a part which involves the cusp forms and Eisenstein series Fourier coefficients, and then there will be a part which will involve Clusterman sums of higher rank Clusterman sums, which corresponds to the Weil element W4, W5, and the long Weil element W6. I'm not going to write down. The main point is that for any relative Tress formula like this, like Kuznetsov-Tress formula, we have a delta symbol expansion. Okay, so that Tress formulas can be looked at as sources of delta symbols. Okay, and sometimes, okay, so this I should write at the beginning. This is a trivial delta symbol, right? So if n and m are of size capital N, and if you're taking q to be larger than n, then you can just take delta nm to be this, because this says that if this is 1 if n is congruent to m modulo q, but n and m being of smaller size q, that will imply that n equals to m, and it is 0 otherwise. So, and even in this trivial delta symbol is also sometimes quite useful. And here is another interesting delta symbol expansion, which comes from the orthogonality of the Bessel function. It's not really coming from any Tress formula. This has been written down by Agarwal, Holowensky, Lean, and Key. And here you'll see the J Bessel function hanging on here, and this is the part which is more or less like the trivial delta function, delta symbol. Okay, yeah. Okay, so there, you can, wherever you see some orthogonality relation, maybe you can get a formula for the delta. Okay, now let me say this, and then I'll give a convexity using delta symbol approach. Okay, so what is the subconvexity problem? It's a little technical. So you start with a cuspidal automorphic representation. Okay, so so pi is a cuspidal automorphic representation for, say, GLDAQ. So it's a rank D automorphic form. Okay, and then there is an L function associated with it, which is LS pi. Okay, and this has a Dirichlet series expansion and a Euler product in certain half plane. And we know from in generality that it extends to an entire function and satisfies a certain functional equation, which looks like this. Okay, this is a Riemann type functional equation, right? And yeah, so where this lambda s pi's are completed L functions, so you have the L s pi multiplied by some certain gamma factors. Okay? And then from the functional equation, so in the subconvexity problem, you are interested in bounding the L function inside the critical strip. From the functional equation, you can get what's called a convexity bound, which says that the L function at the point T in the central line is bounded by the conductor to the power 1/4. Okay, and the formula of the conductor is this, which involves quite a few things. So one is q pi, which is the level of the form pi, and it also involves the spectral parameters kappa j, which appears in the gamma factor, and it also contains the t, the location of this function on the central line. Okay, so that's the formula for the conductor. Okay, so trivially you get that the L function is bounded by conductor to the power 1/4, and you want to get an improvement over that. And we are hoping to get such an improvement because the Riemann hypothesis implies what is called the Lindelof hypothesis, which says that the L function should be bounded by the conductor to the power epsilon for any epsilon positive, okay, which is something very strong. Okay, so the subconvexity problem has a long history, and it really goes back 100 years. The first result is due to Hermann Weil and Hardy and Littlewood from 1920s, and they were looking at the Riemann zeta function, and the Weil bound was that the zeta function at half plus it is bounded by t to the power 1/6 plus epsilon. Okay, and over the 100 years since then, we have improved the exponent, but as you'll see, the improvement is quite mild. We have improved So because the trivial bound was 1/4, so while in one go improved it to 1/6, and in the last 100 years we have been improved it to 1/6 minus 1/84. Right? So this is due to Bourbon. Okay, and it's quite recent. It's from 3 years back, or maybe 2 years back, 2018. Yeah, so I'm just mentioning some landmark results in subconvexity. I'm not going to tell you all the results. That's not possible. Some landmark results only. Okay. So next I mentioned Burgess, which is from 1960. So Burgess looks at the Dirichlet L function. So chi here is modulo q. Okay, so this is a primitive Dirichlet character modulo q. And again, q to the power 1/4 is the trivial bound. And Burgess proved that it's bounded by q to the power 3/16. Okay, so and he used the Riemann hypothesis for finite fields. Okay, to get this, or Riemann hypothesis for curves, finite fields. And the exponent has been improved. So it was first improved to 1/6 by Condrey Vanich in their celebrated work. And very recently, Ian Petro and Matt Young could extend the argument of Condrey Vanich a very different way to get the Weil exponent 1/6 here. Okay, so this was for a long time, this 3/16 was a record, but now we have the Weil exponent. Okay. So this is a work still to appear. And next I mentioned the work of Anton Good from 1980, who showed that this is bounded by, if you look at, so he's working on GL2L function. So here if is a modular form or mass form. So he Good only did it for level 1, but then it has been generalized to general level and Nementippus. So if you look at the L function at half plus IT for a degree 2 of a GL2L function, then this is bounded by t to the power 1/3 plus epsilon. Okay, and this corresponds to the Weil bound, because this L function is like the square of the zeta function. Okay, so for zeta we had 1/6, so the square of zeta will be bounded by 1/3. So this corresponds to the Weil bound. Okay, and this is still awaiting improvement. Okay, so in the last 40 years, we haven't been able to improve it. And then let me mention the work of Ivanich, Friedlander Ivanich, and Duke Friedlander Ivanich in a series of papers, or starting from sometimes late in 1980s, going up to 2001 or 2002. They proved the subconvexity for degree 2L function in various aspects, including the level and the spectral aspect. Okay, and then there are works by Michel, Kowalski, Michel, van der Kam, and Harkos, Michel. They worked out the case for a Rankine-Selberg function. So this is the F and G are two GL2 forms. You look at the Rankine-Selberg function, and they got the subconvexity in the level aspect. And in the spectral aspect, the same problem was tackled first by Sarnak and then by Lau Liu E. Okay. All right, and the nice thing is so the method of Weil and Burgess was different. So they were just looking at one L function, and their goal was to get a bound for that individual L function. From Good onwards up to Sarnak here, these are all based on what's called the moment method. And amplification. Okay, so it's a completely different approach. And then in 2010, there were a series of papers, first by Bernstein, Reznikov, and then by Akshay Venkatesh, and then there was a paper by Michel Venkatesh. So first, Bernstein, Reznikov, and Venkatesh were looking at triple product function f cross g cross h, and they fixed two of them f and g and varying one of them h in the level or spectral aspect, and they got subconvexity. And then Michel Venkatesh looked at the Rankine-Selberg convolution, but over any number field. Okay, so it's a very general setup, and they still managed to get subconvexity over there. Their method is different in the sense that it's called the period approach. So they realize the L value as a period integral and plays with that. Okay, so there is some ergodic theory involved over there. Okay, so you may have noticed that I mentioned GL2 and GL2 cross GL2 and GL2 cross GL2 cross GL2. Okay, so it turned out that the GL3 problem is slightly more difficult. Okay, and it needs some different approach to tackle the GL3 problem. So the first person to look at GL3 with some success was Xiaojing Li, and in 2011 she published a paper where she proved two things. One is she looked at symmetric square twisted by G. So sim squared, if you look at sim squared F, since F is GL2 over here, so sim squared F is a GL3 form. Okay, and G is a fixed GL2 form over here. So this is a GL3 cross GL2 Rankin-Selberg convolution. Sorry, GL2. And if you fix the symmetric, the F part, so if you fix this GL3 part and vary G, then she proved subconvexity in the spectral GL2 spectral aspect. Okay, and from there she derived that if you look at L half plus IT of same square, so this is just a GL3 L function. Okay, and then she proved subconvexity in the T aspect. Okay, so there are two results which followed, and her method is also based on moment, computation of moment, and adaptation of Condry-Ivanich idea. Okay, and then the main point is that she has to restrict to symmetric square L function, and not she cannot work it out for general GL3 function because she needs what's called she needs some non-negativity of central L values. Okay, which is there for symmetric square but not there for general GL3 function. And then let me mention the recent work by Blomer and Butken, where as a preprint from 2015, and they proved that the spectral aspects of subconvexity for a GL3 form. So pi here is a GL3 form. Okay. All right. Okay. So now, so now I'm going to say mention some of my own results and some of the results proved by my students, my postdocs, people in my group, and so we proved subconvexity results using the delta symbol approach. So we want to transform the subconvexity problem to a problem about computing correlation, and then we apply the recipe that I mentioned to show that the correlation is small. Okay, so here is one concrete example just to see how we can apply the delta symbol to deal with subconvexity. So suppose I take delta to be the Ramanujan discriminant form, as the thing everyone knows about. Right, it's a cast form of full level and weight 12, and let chi be a primitive Dirichlet character modulo p, and I'm looking at the L function ls delta twisted by chi, which for real part of s greater than 1 in that half plane is given by this Dirichlet series. Tau n is the Ramanujan's tau function, right? Sorry, I should divide by I should divide by n to the power 11 by 2, okay, because tau n's are of size n to the power 11 by 2. Yeah, because I have to look at the normalized Fourier coefficient. My center is always at half. Okay, and Hecke proved that this can be extended to an entire function, and it satisfies a functional equation, and the conductor is p square. Okay. So if you go back to my the general setup for so there's this conductor in this case is p squared if I keep my t fixed. Okay, so if I'm just looking at the central point, for example, otherwise I should say it's p squared t squared. Maybe it's better to say it's p squared t squared. Okay. Okay, and then from the functional equation you get a bound for the L function inside the so here I should be looking at sorry about this. So L half delta twisted by chi. So I'm looking at the L function on the central line. Then from the functional equation, I can derive that this is bounded by this correlation sum normalized by root n and this. So n has to go up to q, where q is the, sorry again. So Yeah, I took P and then I changed Q. So this is P. Here it's P. Okay, N goes up to P, right? And here, if you just plugging the trivial bound, we know that tau n's are bounded by n to the power epsilon. So you'll see that this correlation is bounded by n. So n by root n, that's root n. So it will be bounded by square root of P. Okay, and so this L function at the central point is bounded by P to the power 1/2 plus epsilon trivially, and that corresponds to the convexity bound. Right? So if you want to get a subconvexity bound for this L function, what you have to do is you have to show that there is some cancellation in this sum. Okay? And that you can expect because the chi-n's are oscillating and the tau-n's are also oscillating. And so, and we expect that the tau-n's are, since tau-n's are coming from a GL2 source and chi-n's are periodic and they're coming from a GL1 source, they should not be correlated. Okay, so and so in most subconvexity problem, you can reduce the problem to computing correlation of this type. And using this idea, I could prove the T aspect subconvexity for GL3 form. All right. So I'm just going to mention some of the results, and then I will mention one new result and give a proof of that. Right? Okay, so here pi is a general GL3 form. So recall that Xiaoqing Li had a symmetric square. She couldn't take a general GL3 form because she needed non-negativity. In this approach, you do not need non-negativity because you're just looking at that individual L function and you're not trying to compute a moment or anything. Okay. So T to the power 3/4 is the convexity. I got 3/4 minus 1 by 16. And incidentally, this is the same bound that Xiaoqing had for symmetric square. Okay. So though we came from two different direction, we ended up getting the same bound for the L function. And I also, in another paper, proved the twist aspect. So here, my GL3 form pi is fixed, and chi is modulo P, and P to the power 3/4 is the convexity, and I got P to the power 3/4 minus something, 1 by 308 or something over here. So at some saving, okay, and this has been improved to 1 by 36. Okay, and so I got some new results for GL3 L functions, but it also turned out that you can use this idea of delta symbol and get the old Burgess bound and Weil bound for the lower degree L functions also. Okay, so it also gives you the results that the landmark results that you had already in the literature. And also it turned out that one can extend this idea to GL3 cross GL2 L functions also. So this is the Rankine-Selberg. So pi here is a GL3 form, F is a GL2 form. I'm looking at the Rankine-Selberg L function, so it's a degree 6. So by functoriality, this is a L function for a GL6 automorphic form. T to the power 3/2 is the convexity. I proved that it's T to the power 3/2 minus 1 by 52. Okay. And the nice feature here is that you can take one of them, pi or f, to be an Eisenstein series. And when you do that, so suppose you take pi to be an Eisenstein series, then this will be the cube of L½ plus ITF. So that will give you the subconvexity for the GL2 L function in the T aspect, not as strong as Goods bound. Or you can take f to be an Eisenstein series, then it will be just the square of a GL3 L function, and you get a subconvexity. So you get something like this, but not as strong an exponent like that. Okay, and another recent result I showed. Okay, so for a long time, the symmetric square L function, it's really a big problem. So if you look at LS sim square f, the big problem is to get subconvexity for such L function in the level aspect and spectral aspect, because this is related to what's called quantum chaos or quantum inequality. And for some time, I had been looking at the central value with f of level p. Okay, then is bounded by p square. P square is the conductor. It's bounded by root p. Okay, that's the convexity bound, and you want to improve it. It's quite difficult, and we still don't know how to improve this p to the power 1/2. But it turns out that if you introduce a little perturbation, so if you introduce, instead of looking at half, if you go up the central line a bit, right? So instead of, so this is the critical strip. So this is the central point. So I want to get the bound of the cell function at this point, but I cannot do that. But if I go a little bit higher up here, half plus IT, then I can get a subconvexity bound, right? So I can get a subconvexity bound anywhere up here or anywhere down here, but not near the central point half, where we really want the subconvexity result. Okay, but it's kind of interesting that we can get something like that, because t can be anything as long as t is larger than p to the power delta, and delta can be really small, like 1 by a billion. Okay, and still we can get subconvexity. Okay, so now we mentioned some results of some of my students. First, Prahlad Sharma, he proved the subconvexity for GL3 cross GL2 twisted by chi. Okay, so and then my other student Sumit Kumar proved the GL3 cross GL2 L function in the GL2 spectral aspect. So this generalizes the old result of Xiaoqing-Li, because Xiaoqing had pi to be just a symmetric square, not a general GL3 form, but in Sumit's result, you can take pi to be any general GL3 form and can get. Okay, in another work, they look at Kumar Singh and Malesham. Look at the GL3 spectral aspect part of this, and they showed that you can get a subconvexity in the GL3 spectral aspect for as long as the parameters, Langland parameters, are near the walls of the Weil chamber, some of the walls of the Weil chamber. Okay, it's not in the generic location. Okay, so because I have to, yeah. So I'll just briefly mention there are many other people who are working on this approach, delta symbol approach, to get compute correlation and to get subconvexity or result towards shifted convolution sum problem. Holowinski, Nelson, Raju Agarwal, Lin, Key, Soon, Fan, Kowalski, Michel, Savin, Chow, and many others are doing that. Okay, so finally, yeah, in the last 10 minutes, I'm just going to mention my new result. Okay, so it's again about GL3 cross GL2 L function, but now it's in the level aspect. So I'm writing it down jointly with my student Kumar and my former postdoc Shourav Singh. So the setup here is that I have a GL2 form F, which is level P1. I can take P1 to be a prime. I have a GL3 form pi of level P2. Again, I'm going to assume that P2 is a prime. Okay, and then the conductor is given by P1 cube P2 square, right? Because this is GL2 as and this is GL3, and this is level P1, so the P1 gets cubed, and this is of level P2, and P2 gets squared because this is GL2. So P1 cube P2 squared is the conductor. And so the from functional equation, you get a c to the power 1/4 as the convexity bound, but we prove that we can get a subconvex bound as long as the two primes P1 and P2 are in certain range. Okay, so as long as P2 is larger than square root of P1, but smaller than 3/2, P1 to the power 3/2. Okay, we have subconvexity, and this delta will depend upon where P2 is located. So if it's like P2, if P2 is very near to square root of P1, this delta will tend to 0. Or when P2 is very near to P1 to the power 3/2, it will tend to 0. But if P2 is sufficiently in the middle, say P1 equals to P2, then you get a nice saving. So you'll have delta a nice positive number. Okay, so let me just sketch the proof. It's quite simple, as I said. So the recipe is, first you reduce the problem to a correlation computation problem. So that comes from the functional equation, because the functional equation says that this can be bounded by this, where these are the correlation sums that are appearing. There's a correlation, so I have to compute the correlation of the Fourier coefficient of f with the Fourier coefficient of pi. okay, where the length n will go up to square root of the conductor. Now, since I'm just trying to get a subconvex bound, I'm not really interested in improving exponent at the moment. I can just concentrate n near square root of the conductor. So my n is between c to the power half minus 2 delta and c to the power half. Okay, and then the error term is c to the power 1/4 minus delta. So as long as delta is something positive, this is nice, this is subconvex, and I need to get cancellation here. If you take the trivial bound over here, you get convexity. Okay, so step one, I separate the oscillation of lambda fn and lambda pi m by introducing a delta, right, delta symbol. And then I use an expansion of the delta. Here I'm using the Duke-Friedlander-Ivanich delta method, which is really writing it down in terms of trigonometric functions. Okay, so my q is going to be square root of n, square root of the size of the equation. Okay, so and then okay, so now n sum and the m sums are nicely separated because this is basically e of an by q and e of minus am by q. So n and m are completely separated. Okay, so now I look at the n part. So here I can apply the GL2 Voronoi summation formula. This is what you get by GL2 Voronoi summation formula, the standard formula. If you apply the GL3 Voronoi summation formula to the other sum, then this sum reduces to this. Okay, so you have to keep track of the lengths. So the first sum has reduced from capital N. So recall that capital N was square root of C, and C1 was P1 to the power C1 was P1 to the power 3, P2 to the power 2. So P1 to the power 3 by 2, P2. So that's my N. Okay. So from that, it has reduced to P1. So you surely have gained a lot over here. And from this, you have reduced it to P2 root n. So here also you have gained. So in these two steps, you have gained a lot. Okay. So so how much do you need to save? So if you so now I'm writing Sn like this. And since I have sacrificed the equation over here, I've lost an n. Okay. So what I have to do is I have to gain back this n. I have to save n. I have to save a little extra to get subconvexity. Right. All right. So I have saved something over here. I've saved something over here. We'll see how much we have saved. And now if I look at the A sum, and this is the nice feature of looking at the GL3 cross GL2 Rankin-Selberg convolution, is that we had this after Voronoi, GL2 Voronoi, and we had this Clusterman sum after GL3 Voronoi. If you do the A sum now, the A sum which is coming from the circle method, it nicely reduces to an exponential, okay, with a bar, n bar, and with just an m. Okay, so n was the GL2 variable, m was the GL3 variable. For GL3 variable, it's just in a geometric sum. For the GL2 variable, it's what's called the Clusterman fraction. Okay, so now the more or less the Sn sum has reduced to something which structurally is just this. All right, and now, as I said, I have to keep track of the saving. Okay, so let's see. So in the GL2 Voronoi, I have reduced the length from n to p1. So by standard philosophy, that means I have saved square root of the initial length by square root of the final length, square root of n by square root of p1. In the GL3 Voronoi, my length has reduced from n to p2 root n. So I have saved square root of the initial length by square root of the final length. So this is the saving from the GL3. This is from the GL2 Voronoi. And now in the A sum, you'll see that this part is trivially, if you take the well bound, this is square root of q times q to the power 3 by 2. And this is bounded by q. So I have saved square root of q here. So that square root of q is, for me, is n to the power 1/4 because q is root n. Okay, so far we have saved n by root p1, root p2. I wanted to save n and something more. So it remains to save root p1, root p2, right? And something more. Now, the next thing what you can do is either you can use reciprocity, bring q up, bring the other things down, do the sum over q. That's one possibility. Or what you can do is apply the Cauchy. Okay, by applying Cauchy, you break the curse of involution. Okay, because you have already applied the functions, or you have summation formula to the m and n. There is no way to apply the summation formula to m and n. That will bring you take you back to where I started. So you apply Cauchy, get rid of the GL3 Fourier coefficient, okay? And this is what you put the rest inside. I'm taking the GL3 outside because with respect to the GL3 variable, it's just a, sorry, here I should have an E. It's just a geometric sum. Also should have an E, sorry. Yeah. Okay, and since I have done Cauchy, my task now is to save P1, P2. And now, because before it was root P1, root P2. Okay, now you just open the absolute value square, bring the M sum inside and apply Poisson, or just see that it's a geometric sum. So this is the what you get by opening the absolute value square. And this is the M sum that you are left with. This is a geometric sum, okay? And when you have a geometric sum in the generic case, right, you will save the whole length of summation, okay? And what was the length? The M length was P2 root n. So you'll save, if you say P2 root n, what you need to do is you have to have this larger than P1, P2, because P1, P2 is what you wanted to save. And this happens if P2 is larger than root P1, okay? Now, as I said, this is a generic case because there are cases where you cannot save this much. One such case is the diagonal, right? If n1 equals to n2 and q1 equals to q2, this is basically 0 over here and there is no oscillation. And so you will not save anything, right? So, but if you take n1 equals to n2, q1, q2, then you are saving in the number of point summation over here, okay? And that is precisely, so if you, yeah, so it's root n times p1, right? So that's how much you save in the diagonal. And you also want that to be larger than p1, p2. And that gives you that p1 to the power 3 by 2 has to be larger than p2, okay? So that means as long as my p2 is larger than root p1, but smaller than p1 to the power 3 by 2, both my generic case saving and the diagonal saving are satisfactory, and I get a subconvexity. I save P1, P2, and something extra. Okay, and that gives me this subconvexity result for level. So incidentally, I must mention here that it's still an open problem. So if you look at L half pi twisted by F, pi is a GL3, F is a GL2. Then if you fix one of them and vary the level of the other one, the subconvexity is not known. Okay? So, but if you vary the level in both of them in certain range, you get subconvexity. So that's a nice feature of this result. So with that, I will stop and thank you.
Thank you, sir. So, any questions? So, Krishna, have one question.
Hello, sir. So, I was wondering if you could explain the relation between quantum unique velocity and the subconvexity problem.
Yeah, in this short time, I cannot do that, but there's something called Watson's formula, which in quantum unique ergodicity you have to study some period integrals, and you have to show those period integrals are small. And what Watson's formula do is he writes the period integrals in terms of L values, okay? And the L values that appear are precisely the symmetric square L function, okay? And the symmetric square twisted by a GL2 form. And he showed there that if you get a subconvex bound for the symmetric square and symmetric square twisted by GL2 form, then you get a sufficient bound for the period integrals, and then you get quantum unique ergodicity from there.
Okay, so this is actually a stronger condition. So the subconvexity will imply quantum unique ergodicity, or is it?
No, the convexity will just give you the trivial bound for the period integral. So it will not give you quantum unique ergodicity. You need a subconvex bound. Even a weak subconvex bound will give you a motor neuropsychology. That's what sound does.
Okay. Okay.
Sir, thank you for the wonderful talk here. The next talk is scheduled on time. Let us hang on.